Most objects that pass through our solar system behave the way physics expects them to. They follow predictable paths, they tumble, they vent gas unevenly, they look messy, irregular, and improvised by chance. Nature, on large scales, rarely produces neat patterns, but every so often something arrives that refuses to fit comfortably inside those expectations. In mid-2025, astronomers began tracking a faint object moving through the inner solar system. At first, it looked unremarkable. A dim visitor wrapped in dust, a small coma, a thin tail. The kind of thing that barely earns a headline. Then the data kept coming. As observations improved, scientists noticed something that did not sit right. The object's motion was unusual, its emissions were structured, and its geometry, when carefully isolated from surrounding dust, appeared almost orderly. This object is known as 3I Atlas, only the third confirmed interstellar object ever observed passing through our solar system. Interstellar objects are already rare. They originate from other star systems, shaped by alien environments, carrying histories we can barely reconstruct. Each one forces scientists to test the limits of their models. But Atlas raised deeper questions. Why did its activity appear so stable? Why did its emissions repeat with such regular spacing? Why did probability calculations suggest patterns that should almost never arise by chance? This is not a story about answers, it is a story about tension between expectation and observation, about how science reacts when data refuses to behave. In this investigation, we will follow the discovery of Atlas, examine the measurements that unsettled researchers, explore the competing explanations, and look ahead to a future encounter that may finally reveal what kind of visitor this truly is. Because sometimes the most important discoveries begin with discomfort. The story of Atlas begins quietly, the way many major discoveries do. In July 2025, automated sky surveys flagged a faint moving object against the background of distant stars. At first glance, it appeared no different from thousands of small bodies catalogued every year, but its speed stood out. It was moving too fast. Astronomers quickly began calculating its orbit, and almost immediately something became clear. This object was not bound to the sun. Its path followed a hyperbolic trajectory, meaning it was passing through once and would never return. In simple terms, it came from outside the solar system. That alone made it extraordinary. Only two such visitors had ever been confirmed before. Each one sparked intense debate, not because of what they were, but because of how little we know about material formed around other stars. Follow-up observations began almost immediately. Radio telescopes, optical observatories, and tracking networks worked together to refine its motion. Facilities like the Green Bank Telescope helped monitor emissions, while the Deep Space Network assisted with precise trajectory measurements. As the data improved, scientists could confirm the object's interstellar origin with high confidence. Its velocity was far too great to be explained by gravitational scattering within our system. It had entered on a steep angle, slicing through the planetary plane instead of drifting along it. Atlas was a true outsider. Early interpretations were cautious. Based on brightness and behavior, researchers classified it as a comet. As it approached the sun, it developed a surrounding cloud of gas and dust. Solar heating appeared to be activating frozen material on its surface, exactly what would be expected. For a moment, the discovery seemed straightforward, but deeper analysis changed the tone. As imaging resolution improved and data was processed more carefully, astronomers noticed that the object's activity was not chaotic. Instead of irregular bursts of gas, its emissions appeared persistent and repeatable. This was not obvious in raw images. Only after applying advanced filtering techniques did the structure emerge, and once it did, the initial comfort of classification began to fade. Atlas was behaving like a comet, but not like any comet scientists were used to studying. The discovery shifted from excitement to curiosity, and then to something closer to unease, not because the object was threatening, but because it refused to behave casually. By the end of the discovery phase, one thing was clear: finding Atlas was not the breakthrough, understanding it would be. To understand why Atlas became so puzzling, it helps to understand how scientists study objects this small and distant. Astronomers rely on a combination of imaging, spectroscopy, and motion analysis. Imaging shows shape and brightness. Spectroscopy breaks light into wavelengths, revealing chemical composition. Motion tracking reveals rotation, acceleration, and subtle forces acting on the object. In the case of Atlas, all three methods delivered surprises. Spectral analysis confirmed the presence of common cometary materials: water vapor, carbon-based compounds, and dust grains consistent with frozen bodies warmed by a star. Nothing about its chemistry screamed exotic, but chemistry was only part of the story. When scientists isolated the inner coma, the cloud of material closest to the nucleus, they noticed narrow jets of gas emerging from specific regions. Jets are normal in comets. They form when sunlight heats volatile pockets beneath the surface. What was not normal was their organization. Instead of appearing randomly, the jets were few in number, sharply defined, and persistently spaced at nearly equal angles. As the object rotated, the jets maintained their relative positions, suggesting a stable internal structure. Symmetry in nature exists, but it is fragile. On objects battered by radiation, collisions, and thermal stress across millions of years, symmetry usually breaks down. Probability estimates attempted to quantify this. While exact numbers depend on assumptions, the likelihood of multiple independent vents aligning so evenly, activating with similar strength, and remaining stable over time is low, not impossible, but unlikely. Trajectory data added another layer. Atlas showed subtle non-gravitational accelerations. These could be explained by outgassing, jets pushing against the object like tiny thrusters, but the direction and consistency of these forces raised questions. Normally, cometary outgassing produces erratic motion. Jets turn on and off, surfaces erode unevenly, rotation becomes chaotic. Atlas did not tumble. Its rotation appeared stable. Its emissions appeared controlled, or at least constrained. Scientists proposed natural explanations immediately. One idea was a contact binary, two or more fragments fused together gently long ago, creating preferred vent locations. Another suggested layered volatiles buried beneath insulating material, forcing gas to escape through fixed channels. These explanations are plausible. They are grounded in known physics, but none of them fully account for the combination of stability, geometry, and timing observed. Importantly, scientists emphasize restraint. Data does not imply intent. Patterns alone do not equal design. Nature is capable of producing outcomes that feel improbable to human intuition. Yet the classification remains unresolved. Atlas is not labeled artificial. It is not labeled anomalous technology. It is labeled something quieter and more uncomfortable, unusual, and in science, unusual is often the most dangerous word, because it means the models work until they do not. When data resists clean explanations, science does what it always does. It expands the hypothesis space. The first and most conservative explanation is that Atlas is a natural object, a comet or asteroid ejected from another star system. In this view, its behavior is rare but not unprecedented. Given enough time and enough objects, improbable configurations will eventually occur. Layered internal structures could channel gas through stable vents. Rotation could lock emissions into repeating patterns. Contact binaries could create geometric coincidences. These explanations rely on known processes. They require no new physics. Their weakness lies not in impossibility, but in accumulation. Each individual feature is explainable. The challenge is explaining all of them at once without fine-tuning. This is where alternative speculation enters. Some researchers have raised the possibility that Atlas could be artificial in origin, not a spacecraft in the cinematic sense, but a probe or fragment designed to survive interstellar travel. This idea is not presented as a conclusion. It is presented as a question. Artificial objects prioritize efficiency. Symmetry distributes forces evenly. Stable rotation reduces stress. Controlled outgassing could double as propulsion. These features are familiar to engineers. They are less familiar in kilometer-scale debris. Critics of this idea are quick to point out the lack of direct evidence. There are no signals, no materials inconsistent with natural chemistry, no maneuver that clearly violates physical law. Supporters counter that absence of evidence is not evidence of absence, especially when observing distant, inactive, or degraded technology. The key point is not which explanation is correct. The key point is that both leave unanswered questions. If Atlas is natural, it represents an extreme case of organization arising from chaos. If artificial, it represents something far more profound, a relic from a civilization we may never detect again. Science does not choose sides here. It weighs probabilities, updates models, and waits for new data. Speculation is not belief. It is a stress test for understanding. And right now, Atlas is stressing our assumptions. The future of the Atlas mystery hinges on a single event. In March 2026, the object will pass near Jupiter. This matters because Jupiter is not just another planet. It is a gravitational giant. Its tidal forces can tear apart loosely bound objects or dramatically alter their trajectories. Scientists view this encounter as a natural experiment. If Atlas is a fragile comet, Jupiter's gravity could disrupt its structure. Jets may shift. Rotation could destabilize. The nucleus might fragment. If Atlas remains stable, maintaining its geometry and emissions under intense stress, that information alone will reshape interpretations. Researchers will watch for changes in spin rate, jet alignment, and non-gravitational acceleration. Even small deviations will carry meaning. Importantly, predictions remain conditional. Science does not expect surprises. It prepares for them. This flyby is not a verdict. It is a data point, but it is a powerful one. Whatever happens near Jupiter will either ease the tension around Atlas or deepen it. Atlas began as a faint dot. It became a trajectory. then a classification, then a question. Along the way, it reminded scientists of something fundamental. Our models describe most of the universe most of the time, but they are not complete. Interstellar objects are messengers from places we cannot visit. They carry information shaped by alien stars, alien disks, and alien histories. Most will pass quietly. A few will demand attention. Atlas is one of those few. Whether it turns out to be an exotic comet, a statistical outlier, or something no one has yet imagined, its value lies in the challenge it presents. It forces us to ask better questions, to sharpen our tools, to admit uncertainty. Science does not fear mystery, it feeds on it. As Atlas continues its journey, the data will improve, the models will adjust, some theories will fall away, others will strengthen, and perhaps the most important outcome will not be what Atlas is, but how carefully we learn to listen when the universe whispered something unexpected. Because if this is only the third interstellar visitor we have noticed, how many have already passed unseen, and how many are still on their way?